Welcome to IPMWORKS e-learning modules. My name is Ellie Dearlove from ADAS, and this video is part of Module 5, Invertebrate IPM. We will present Chapter 5.4, Decision Support Systems and Monitoring as part of Invertebrate IPM. This chapter summarises the role of decision support systems and in-crop monitoring as part of Invertebrate IPM. This chapter is divided into two parts, first on decision support systems and then on crop monitoring. The aim of this chapter is to highlight the important and best practice for using decision support systems and crop monitoring for Invertebrate IPM. We will cover what decision support systems are and how to use them, and secondly, why crops need to be monitored and how to do it. Before we consider decision support systems and monitoring, it's important that Invertebrate IPM is undertaken with a wider view of all potential pests. Key pests should be identified at the start of the season and should reflect the likelihood and impact that potential pests could have on each crop. This can be done using a simple scoring system for each pest. This separates out pests most likely to infest the crop and have an impact on crop performance. Growers should have a plan in place for any pests that may infest or are likely to infest crops, and any pests that may or are likely to lead to economic injury, which is any pest with a moderate or higher overall risk score. This review process should be done annually and should be used to target selection of appropriate decision support systems and monitoring techniques for the season ahead. If we consider an example of the risk of orange wheat blossom midge, which is an occasional pest of milling wheat in the UK. While it often occurs in crops, only where it infests the crop during ripening does it cause economic damage, and even then only at high levels. Management may be needed if the midge emerge around vulnerable crops and where there are low numbers of natural enemies, so monitoring in crops is recommended. This could be assessed as giving the pest a likelihood score of 3. i.e. may infest, and a hazard score of 3 may lead to some economic damage. However, there are resistant varieties of wheat available. Where these have been used, the hazard score is different. It's unlikely that infestations will lead to economic injury, so give a score of 1. In this case, the overall score would be 3, low risk, and so in-crop monitoring may not be necessary. This risk estimation is specific to individual farmers and their crops, as the estimation of likelihood and hazard are relative to individual circumstance, changing both between farms and over time. Successful IPM systems depend on effective decision-making associated with the selection and implementation of strategic, tactical, and operational techniques. Strategic systems are usually holistic. They're applied at the whole farm level across all pests. They prioritize and coordinate application of multiple IPM approaches. Tactical systems are usually applied at specific crop pest targets and support users in assessing and responding to risks by providing guidance based on observations or calculated forecasts of pest activity. These include observation networks, forecast models, and economic thresholds to support pest management decisions. Operational systems are designed to enable rapid response to in-field observations and usually consist of guidance associated with dynamic thresholds. Whether they are strategic, tactical, or operational, decision support systems provide guidance on what steps to be taken to identify and reduce the risk of crop damage by pests. Decision support systems must be used alongside in-crop monitoring, which will be discussed in Part 2. Next, we'll provide a summary of each type of DSS with examples and points on where you can go for more information or to access free decision support systems. Strategic techniques require many farm-specific considerations and therefore tend to be generic guides to improve the overall IPM uptake. The main type of strategic DSS are farm-level guidance, helping growers to identify key approaches relevant to their farm. For example, LEAF's Sustainable Integrated Pest Management Guide and Scoring System in the UK. Tactical DSS are the most widely used systems and consist of two types: observation networks and risk forecast systems, which will be discussed in the following slides. We will not include here systems that automatically implement management practices based on underlying pest or crop models. That's without farmer or advisor review. Observation-based risk assessments report the presence or absence of a pest at field scale at a given time. Typically, they report risk maps or tables of specific pest occurrence over time. They are usually based on ongoing regional networks that routinely and consistently monitor specific high-risk pests. The aim is to provide up-to-date real data on the presence and absence of key pests during the year, acting as a warning for likely pest activities in the surrounding area. In Norway, a long-standing platform known as VIPS reports on several observations of reports made from across the country. This is combined with risk forecasts to provide growers and agronomists with a detailed overview of current and future risks. International observation networks can be highly valuable for migrating pests, which may only occasionally appear in certain regions of the wider migration area, but still have a large impact on crops. The diamondback moth, Plutella xylostella, is a pest of brassica crops, including oilseed rape. The diamondback moth does not overwinter very successfully in northern parts of Europe, and infestations in early summer usually arise as a result of migrations from continental Europe. These occur when the wind direction is favourable and when there is a large population of moths ready to migrate. In this case, it is beneficial for regional networks to pool information to help growers to assess the likelihood of arrivals in their crops and prepare suitable monitoring and management options. Risk forecast systems use mathematical models to predict pest activities. Typical information provided into these systems include weather data, most often air temperature and rainfall, but also wind speed, air humidity, soil temperature at various depths, and other factors are often used. Plant growth stage and the first site of a particular stage, for example, the date of the first observation of adults of the relevant pest that year. The mathematical model, or the algorithm, is developed based on validated observations of the pest in crops, and it makes various assumptions about the relationship between the pest's ecology and these environmental conditions. When interpreting the outcome of a risk forecast system, be sure to check that these assumptions apply. Risk forecast systems normally report a level of risk on a specific event occurring, such as the emergence of a pest from a given life stage or a migration event. Some systems also provide guidance or suggested management action, but these outputs should always be interpreted and applied in the context of information available in your crop. Use of monitoring techniques is highly recommended alongside the use of risk forecast systems. The codling moth, Cydia pomonella, is a pest of worldwide importance that exhibits seasonal phenology that's mainly affected by temperature. It causes damage to the fruit of apples, pears, and other pom fruit. Larvae emerge from eggs that are laid on the surface of the fruit and they burrow inside. The surface blemish can reduce fruit value, and any internal damage renders the fruit unsellable. A simple degree-day phenology model has been developed for the Mediterranean climate, describing moth phenology of all three male flights. Based on field data collected in several locations in several years, the first males of the first overwintering generation were caught between 250 and 300 degree days, and the population peaked at 468 accumulated degree days. Similar predictions could be made for the second and third emergence events. By predicting the appearance of the moths, targeted monitoring can be implemented so that the need for treatments can be accurately assessed and better timed if necessary. This supports reducing monitoring effort and improved management. The codling moth risk forecast is one of the many freely available systems on the EU-funded IPM Decisions platform. The platform offers free risk forecast systems for any location in Europe and provides links to other region-specific or pay-to-use systems. Visit the link on screen to set up an account. The final type of DSS are the operational systems. These are effectively in-field decision support systems that help in final decisions on where further management may be required. These consist mainly of economic thresholds, requiring information from in-crop monitoring to guide the farmer and advisor on the potential for a given pest infestation to lead to economically damaging levels. The challenges of developing trustworthy thresholds was introduced in Chapter 5.1. As with all DSS, thresholds should be applied with caution and interpreted within the context of each crop and pest interaction. Most thresholds are static. They provide a fixed number of pests per unit area or plant, above which treatment is considered justified. More recently, dynamic thresholds are being developed that account for aspects of crop conditions, such as those for pollen beetle in winter oilseed rape. Pollen beetle damage oilseed flower buds, breaking them open to access the pollen inside. Winter oilseed rape produces more flower buds than it needs to achieve profitable yields in an arable system. Knowing that the plants can tolerate some loss of buds to pollen beetle, we can allow the pollen beetle to feed on some of the buds without any impact on the farm yield being apparent. We also know that the number of buds that oilseed plants can tolerate being lost is proportionate to the size of the plant, or more importantly, the density of the crop. The figure on the left represents how many pollen beetles a crop can tolerate before any effect on yield will become apparent. Previous research has shown that the higher the plant density, the lower the number of flowers per individual plant, and we also know that a single pollen beetle will consume on average 9 flower buds per plant. So, bringing this information together, we can measure the plant density at the risk window for pollen beetle, which is the green bud stage, and gain an estimate of how many pollen beetles the crop can tolerate before any negative effect will be seen. Decision support systems help growers and agronomists to recognise, understand and interpret the risks and associated management options for crop pests. There are a range of systems available and all should be used with care and in the context of crop monitoring observations to ensure that effective decision making as part of an IPM strategy is taken. Everything varies in nature, and given this underlying variation, how can we make management decisions? Even if all the fields were treated exactly the same, we'd expect variation in species diversity and abundance within and between them. This is influenced by soil, aspects surrounding landscape, climate, etc., etc. The most advanced decision support systems will not be able to make 100% accurate forecasts of every pest in every part of every field. In order to plan management options and to assess the impact of management practices, collection of actual numbers of pests is essential. Information on pest numbers at different locations is also needed to be able to make an informed assessment of pest populations at relevant spatial scales, to give confidence that any difference seen is not a result of natural variation, to be sure that high number of pests seen at one location is also seen elsewhere. The challenge for monitoring pests and their beneficials is that the natural variation of any species of interest is likely to be very high and patchy. For example, with many locations where no pests are seen and a few places where lots are seen, especially early in the season. This variation is influenced by different factors at different scales, and those factors impact on pests and their natural enemies in different ways. In-crop monitoring is essential to make effective decisions on pest management, relevant to the conditions at a specific location and based on predetermined thresholds for action. Monitoring is a time-consuming and costly activity. Not all pests can be monitored in all parts of every crop. Based on an initial risk assessment, an appropriate level of monitoring can be determined for each pest. The type of monitoring will change based on each location and throughout the season. There are 3 types of monitoring. The first, observation, applies to all pests identified as posing a potential risk of economic injury. For many pests, crop injury only occurs in some seasons under certain conditions. Where available, observation networks and decision support systems, which were covered in Part 1, should be used to guide if and when in-crop monitoring is required. During vulnerable periods of infestation, crops should be inspected for pest activity during regular crop walks. If pests are observed, monitoring should increase from observation to recording mode. The second is recording. Where infestation and damage are likely, in-field monitoring is needed to collect real information about pest activity in the crop and inform management decisions. It's important to record this information in a way that can be easily reviewed later on, including the location and the scale of pest occurrence. There are standard methods for recording pest numbers, but the most important thing is to be consistent between people and over time. Finally, reviewing is a critical part of monitoring and involves the interpretation of the information collected, putting the observations into the context of management decisions. This should be done across all pests in the crop to make effective holistic management decisions. Advanced analysis may require the use of data analysis software and should be discussed with a trained advisor. Sharing reliable pest information within a local network can aid in both alerting each other on early sightings of key pests and interpreting individual observations in the context of wider pest pressures. This is best done during the season, but it can also be done as a reviewing exercise at the end of the season to understand where improvements to management could be made. Observations should be carried out in a way that can be repeated on a regular basis, and ideally which can be carried out by different people following an agreed standard approach. This ensures that numbers collected by different people on different days can be compared. Without a standard approach, it's impossible to tell if differences in numbers of pests is seen because of changes in pest population size or differences in the way in which the information was collected. For example, aphids are usually found in higher numbers on the underside of leaves. If observations are made first only on the tops of leaves, and then on the top and bottom of leaves in a different field, the results will be very different and give a false presentation of the relative risk in each location. Regular crop walks are an invaluable way of carrying out general observations. The risk that pests present can be dependent on the growth stage and the condition of the crop, as well as the presence of other pests and beneficial natural enemies. In-field observations should be complemented with information from regional observation networks and decision support systems where available. During a crop walk, be sure to visit as frequently as you can. Pest activity can change quickly, and regular, frequent visits to see changes in abundance gives a better indication of the potential risks than just one-off visits. Stop and look at all parts of the crop and not just at the field edges. Invertebrates often hide under leaves, on stems, or at the base of plants. Take photos. If you see something you don't recognize, try and find out what it is. And finally, record what you find so that you can go back to the information later. Don't just rely on your memory, make sure to write it down. Where the risk of crop damage is increasing, observations may not be enough to effectively inform management decisions. Monitoring involves a more systematic approach to information gathering and ensures that decisions are made based on actual risk to crops. The type of monitoring required depends on the pest targeted, and in some cases the best approach will still be direct counts of the pest on the crop, as this is the case for many economic thresholds. For other pests, an indirect approach might be needed, using collection techniques. Information on pest numbers should be taken from across the crop, ideally taken from 30 or more locations following a W pattern to avoid being too heavily influenced by pest activity in a small part of the crop. Where there is a risk of crop damage, a series of observations should be taken over time to enable a review of the change in pest numbers. Infestations can resolve naturally where there are sufficient natural predators in the landscape. Practicalities and time restraints often mean that it's not possible to do this, but in all cases, monitoring should be undertaken at both the field edge and field centre in a representative part of the crop. Collection techniques range depending on the pests, generally including on-plant assessments or the placement of baited or unbaited traps, which need to be checked against a predetermined threshold to inform management decisions. Where available, economic thresholds should be used to assess the need for management interventions. As we said before, everything varies. The pest pressure on one field can be different from neighbouring fields and between farms. This can be linked to fundamental differences in locations, such as soil type or cropping history, but it can also be linked to management. By reviewing on-farm observations in the context of changes between locations and over time, and sharing that information with neighbours, it's possible to disentangle the factors that drive higher levels of pest occurrence. This can help to identify and implement more preventative management approaches and supports a transition towards holistic IPM. Summarize, we should identify and prioritise the pests that are high risk at our location at the start of each season. More detailed monitoring gives more confidence, but it also requires greater effort. We should use decision support systems where they are available and appropriate for our crops, and monitor crops at appropriate levels, observing for low-level monitoring as part of regular crop visits, recording when risk increases and increasing monitoring to record pest activity, and reviewing to compare pest activity over time and across locations to improve future management decisions. Remember, everything varies, so monitoring is always recommended. If you would like to access references and resources used in the development of this chapter, please pause here.